Yeah, hello class. We feel very good. Yeah. Now it is another session, and we are back to cover the last topic of senior 2 in the new curriculum. Now, remember we have covered so far 4 topics. That is, we've started with acids, bases, and indicators. That was the first topic. 2, we covered salts. Then 3, atomic structure. So that gave us periodic table, atomic structure. Then we went on topic 4, reactivity series, and finally we are on the last topic, the 5th topic. These topics are 5 but very, very long. They are very long. Now for the case of today, we are starting on for this another broad topic called the carbon in the environment. Carbon in the environment. And that is the last topic in senior 2. So, now there will be carbon in life in senior 3. That means the first topic of senior 3 will be carbon in life. But today we are looking at carbon in the environment. Now, this is so broad. Remember, in our periodic table, we also saw that carbon was among some of the elements in the periodic table. What was the group of that element? They are called carbon. Somebody recalls? It was found in a group. Somebody who can recall? Yes, Patience, you recall carbon was in which group of the periodic table? Group 4. Yeah, group 4. And group 4, that was carbon. Do you also recall the color of that element? The color of that element. The general color of that group 4 element. You don't seem to recall, not so? Now, we shall see under here. Let us first visit its subtopics. The subtopics, are very, very many. And the first subtopic here, we shall look at forms of carbon, in the environment. Forms of carbon in the environment. Form means in which state or what is carbon in the environment. That if you are looking for carbon, you find it as what? Carbon is found as what? And remember that remember that this carbon is almost every natural thing that we have on earth here. See? And remember one of the subtopics I told you that this carbon here is what gives the natural things the name organic. See? We call them organic because they are basically made of carbon. See? That's a very, very important point. See? Wood is organic. Plants, your body is organic. That means your body is basically full of carbon. Now too, we shall look at fuels. Fuels, and under fuel there is a lot. See? That there is a lot. See? A lot. Then we shall also visit the carbon cycle. Carbon cycle. See, then visit the carbon dioxide gas and its properties and its properties. See, now, see, we shall also visit hard and soft water. And you see, we saw this part briefly in senior 1 under a topic called water. See, water. We saw hard water briefly. That's why, if you recall, we did not exhaust, see, the water chemistry of hard water and softy. We suspended it because right now we are seeing it in details. Yeah. Did I start by saying that this carbon here is every natural thing that we have? Yeah. Why are they called organic? Is that because they are made of carbon. Your body is organic. That's why it forms organic manure. To be organic is to contain a high carbon amount in the natural material. See? In the natural material. Forms of carbon in the environment. See? And under here we are going to see the meaning of that word allotropy. Allotropy. See? Allotropes. So allotropes. Yeah. Various forms of carbon. Then differences in the forms of carbon. That means by the end of this lesson you should be able to narrate chemical information on the various forms of carbon. Like if we said go and look for carbon for us, don't say I did not see it. See? Because we are going to see that carbon is found in many forms. It occurs in many forms. See? Yeah. Start with now to discuss this word allotropy. I would like to point you here. Now we are starting on that word allotropy. Allotropy. I'll put you here. I will ask a small kind of. I'll give you a small kind of. A myth that might be possible or not possible. if today, right now, you see me today, see, as a man, let me take, I am a man right now, but a few years back, I was a what? A baby. In some years to come, I will be old with gray hair. Not so? Will I have changed from myself to be Wanyama Joseph? Was I Wanyama Joseph when I was young? And am I the same? Will I be the same when I get old? Will I be still Wanyama Joseph? See, now carbon, listen, very well. Carbon, you don't, carbon is found in very, very many forms. You'll find charcoal at home. Going to see these things. You'll find charcoal. Then you go and find soot in your lamps. We know a lamp?
Yes.
And you'll go somewhere in a dry cell. See, in a dry cell, and when you open it, you'll see the middle rod there. What's the middle rod in the dry cell? What's its color? Black. See, this black material. Then you'll see where you'll go where they cut glass. Well, in the industries where glass is made, and they are cutting thick glass by a machine which has a very hard cutting part. See, cutting devices. Then you'll also go drilling devices in rocks. Where the tip, I think you've seen when they are constructing roads, they can cut even chorus. They can cut a tarmac road with a machine and cut part of it. See, and cut. And that part that cuts there is so hard it cuts stones. So you can't get an ordinary method to cut a stone, no? So you realize that all these, you see this is black, soot is black, see, even that is black, and also cutting device for the machines, is it black? Or you haven't looked at it? Have you seen some necklaces made of this?
Yes.
Diamond? How do they look to your eyes? Does it look black? Is it black? How do they look? See, they look very, very sparkling and shiny and attractive. Not so? Don't say it is gold. Gold is yellowish. For them, they are color. They are transparent. Now, all that is the ways in which you find carbon. That means carbon is found as charcoal, soot, diamond. All is carbon. There is a mineral that we talked in minerals one time that it has carbon.
Graphite.
Somebody saying graphite. No, not really. Though graphite is also, now graphite is this material. So now there is a mineral we talked about when we saw minerals and rocks in the last topic of senior 1. We saw a certain mineral that is made of basically carbon. Said limestone. Sorry, I mistook. It was a rock that had carbon, basically carbon. See, that rock is called coal. Now, diamond is not black, but it is carbon. See, all this is carbon. Now, carbon is existing in very, very many forms, but still is a solid. Are these solids? They are solids, not so? Yeah, that's where we are getting our definition here that carbon is existing in very many forms but in the same solid state. See? Yeah. The existence of an element in more than one physical, in more than one form, but the same physical state. Yeah. Yeah. It exists as graphite, a solid, as charcoal, a solid. See? It means existence of an element in more than one form, but the same physical. Physical is that solid state of carbon. Yeah. Now let me ask you a question. If allotropy is the existence, then what are these? What are these? These are now the different forms of an element. The different forms of an element, see, but having the same physical state are allotropes. See, and that is your carbon. So now, we are going to see ahead here that carbon there is strictly, most of these are black. See? And we shall say there that whichever material you burn and it leaves a black residue behind will be showing you that it is strictly carbon. Like if you burnt you burnt what? What do you burn at home, and when you burn you see black? Oil? In cars. When you burn those paraffin, don't you see soot? Soot is black. Now, forms. Now the next discussion is the various forms of various forms of carbon. Now, carbon here has allotropes. See, allotropes are those forms that it has those that are what? Crystalline and to be what's a crystal? Because we saw that definition under minerals. See, to be crystalline, what is it to be? Yeah, to be crystalline.
Like to have a definite shape.
Exactly. With an ordered arrangement of your particles. That means this side they don't have a shape, not so? Yeah. See? Now the crystalline forms here, we have diamond and what? Graphite. Yeah. Diamond is crystalline. It has a definite shape. Even graphite has a definite shape. Now here, non-crystalline, we have non-crystalline form of carbon is called, because you said is to not have a definite shape and ordered arrangement. Now the non-crystalline form of carbon is called amorphous. The word amorphous in English, if you Google there, amorphous means shapeless. I hope your friend will not say you are amorphous. See? You understand that? Don't say you are amorphous, it would mean you are. See? Under these amorphous forms of carbon, we have soot. Is the soot having a shape?
No.
See, it's called lamp black. Lamp black. There are so many. Wood charcoal. Wood charcoal is that charcoal you use at home. Animal what? Charcoal. See, then we left out coal here. Coal. So, coal. That rock, which is gray. See, which is gray. Very hard. See, made of majorly carbon. Yeah, now these are the various forms. To be crystalline is to have a shape and ordered arrangement of the particles in it. Let us start with diamond. Now we are trying to exhaust there. Diamond. So now I'll ask you to put in Google the diamond and you look at it. It's very, very colorless. Can a solid be colorless? What is the color of glass now?
Colorless.
Yes. A solid can be colorless. So, yeah. Diamond is colorless. Okay. Let us look at properties of what? Diamond. It is colorless and transparent. Colorless and transparent. If those ones you can see many from Google, from our Google. That means don't leave behind your smartphones when you are coming for the lesson. And a laptop with a modem. Come with it. Because some of these things we need to see them. We don't have them where we dig them. Because you remember that some of these minerals are found in some countries like what? Like DR Congo has diamond. So it is very hard. In fact, the hardest substance in addition to enamel. So it is very dense with a density of 3.5 grams per cubic centimeter. Very dense with that density 3.5. And these ones I'm going to ask you to Google and we see. So we see. Now we said it has a shape, not so its shape is a tetrahedral shape. Do you know tetrahedral? Four-sided structure. Tetrahedral like this. See? It's tetrahedral shape. Now, diamond is a poor conductor of what? Heat. That means it can't conduct electricity and heat. Yeah. Now, turning to its structure, we've said it is a tetrahedral structure. Yeah. Now we can turn to the structure of diamond here. We are going to exhaust each one. You understand? We have said diamond is not got from an industry. They mine it from underground. It's a mineral. Yeah, it's a mineral called diamond. Now, structure of diamond. Let us discuss over this structure. And also you can see pictures on Google. Now, since we said it's basically carbon, now let me refer you back here to the predictable. You say the carbon is in which group of the predictable? Group 4. How many electrons does it have out?
6.
How many electrons does carbon have?
6.
And somebody who is very sure? Remember, the carbon has atomic number of 6. How many electrons will it have out? 6. How does it have 6? How do you pick electrons? How do you know the electrons out?
It from the number of protons. And the number of protons is
The number of electrons in the whole carbon. Now how many are out? Because these are electrons in the whole atom of carbon. How many will be out? Refer to the first shell has how many? There will be 4.
Yes.
With the configuration of 2 to 4. Yeah, thank you. Now it has 4 electrons out from its configuration of 2 to 4. Not so. Now listen. You see, it has 4. Normally, when you have electrons out, the electrons are what is used to join one atom to another atom. So, now listen, what joins one atom to another atom is called a bond. A bond is a link. That word in chemistry, to link two atoms. When I say carbon is joining to carbon, the line joining them there is we call it a what? A bond. See, a bond, and that bond is called a covalent bond. Covalent bond. See. Now you need to listen very attentively. Now you see the number of electrons out is the number of bonds you form. It's the number of atoms you are neighbored to. That means carbon can be neighbored by how many atoms? 4 atoms. See? But they must have an ordered arrangement because it's a crystal. It must not arrange anyhow you want, you know. You arrange it. Now, seemingly, in diamond, each carbon atom, like if we took this carbon atom, it is neighbored by other 4 carbon atoms. This one will be neighbored by these like this. You see? Then the all other carbons, now you just keep joining more as you extend the structure. See? But you start with a carbon being joined to 4. Each one will be joined to 4 as long as you will be able to arrange 4 bonds around it. 4 bonds. Like here, 4 bonds. Like here, you can have another carbon there, then you arrange 4 other corners like that. See? But in actual drawing, you'll find it drawn well as a 3-dimensional structure in a much more presentable way on internet. I might not be a good artist, but you'll find it appearing, we call it a tetrahedral four-sided structure. You check that appearance on internet. You'll find a colorless shiny crystal on internet, but inside it is this arrangement. Inside it. See? Now, listen, in a metal, what normally conducts heat in substances is electrons. See, listen. Now, electrons, and the electrons that conduct electricity are those electrons which are free to move within the structure of the substance, which are not being used for bonding or for joining to other atoms. Now, in diamond, every carbon atom is joined to 4 other atoms, and all the 4 outer electrons to join to other carbon atoms. That we say carbon bonds to other 4. Every atom here does so. We don't have to draw the bonds because the structure will be so joined up and confusing. Just show a few. Show one carbon center with 4 neighbors. That means it has absorbed all the electrons. None is left free. See, none is left free. See. So, now, what makes a structure to conduct electricity is possession of some free electrons. Carbon here in this case has no electron that it is free. That means carbon has what we call a free moving electrons, therefore it can't conduct electricity. Those free moving electrons are also called mobile electrons. Now, simply, in case you wanted to describe the structure of diamond, we would simply say diamond consists of a tetrahedral structure in which each carbon atom, diamond consists of a tetrahedral structure, see, in which each carbon atom is covalently bonded. That bond is called covalent bond. Is covalently bonded. See, covalently bonded to other 4 carbon atoms, 4 carbon atoms, forming a 3-dimensional structure, of very many covalent bonds. See, now what makes diamond very hard is those bonds, special bonds called covalent bonds, those linkages that are very hard to break. That's why for it can break a metal, the metal can't break it, because it has those ordered, arranged, very many. See, 3-dimensional, we mean a solid that has been developed. See, has this face, the other face, the other face. That is to be 3D. To have all faces and to be a solid with existing faces and sides that can be seen in all directions. Now the question would be, why doesn't graphite conduct electricity? Who has picked something there? Yes, let mentions why shouldn't diamond not conduct electricity?
Because its bonds are too strong that electricity, like it doesn't have free moving atoms that conduct electricity.
See, doesn't have free moving. Now chemistry, yes, chemistry is very specific. Thank you for the correction. Now, you see every bond here is joined to an electron on this carbon. That means carbon is using one electron forms this bond, one electron forms the other bond, one electron forms this one, leaving no electrons to conduct electricity. Why doesn't it conduct electricity? Does not contain free mobile electrons. That English word for mobile is to be delocalized. Sometimes when you are making research, you'll see they will tell you it does not have delocalized electrons. Mobile is to be delocalized. Yeah. Why is diamond very hard?
Covalent bonds that are too strong
to break. That's good. Has very many covalent bonds that are hard to break. Okay, that's very great. Uses of diamond. I hope you drew that simple structure of diamond. Yeah, a hard substance is used for, and that means making devices for cutting what? Stones, glasses, other metals. That means drilling rocks, making tips for drilling rocks, for drilling rocks. See. What else does it? See, what else does that diamond? Yes, it can be used as an insulator since it is a poor conductor of electricity. Yeah. Now, what of? Is there another? Yes, because it is shiny and sparkling, not so? Yeah, making jewelry like what? Like what? I don't see anyone with an earring, not so? Yeah, earrings, bangles, bangles. You know a bangle? Girls, you like wearing those things in the wrists of the hand wrists. Now that one takes us to discussion of graphite structure. Patients, are you really picking these forms? Graphite. What is now that graphite is as I told you that these things, very many of them, we have them on the internet. Or by brainstorm, who has one property? It is crystalline. Yeah.
It's very hard.
It is very hard. Are you sure that inside of a dry cell, that middle part you can't break with your hands? Yeah. It is soft and slippery. So soft and slippery. That means when you touch it, it feels to be slippery is to be smooth, like very fine flour. That means it is a good conductor of heat and electricity, therefore used to make. That middle part of a dry cell is called what? An electrode. A good conductor of electricity, therefore used in making electrodes, like those, that middle rod in a dry cell. It is black and opaque, isn't it? Yep. And opaque. It has a density. That means it is much less dense than what? Than what? Than what? Than it has a density of 2.3, meaning it is less dense than what? Than diamond. See? Than diamond. Structure of graphite. See? Structure of graphite. Now graphite is for it conducts electricity because it must not use all the 4 electrons. See? Now in graphite, you need to listen here very well. We didn't say it has a hexagonal layered structure. That structure, you left it out in the properties. Hexagonal layered, that means it has layers of hexagons. So yeah. Now if you look at graphite structure is funny, and I will ask you to observe it on Google very, very well. It has hexagonal rings which are in form of hexagons. But remember that each carbon has 3 other neighbors. Leaves out one what? See, I don't know, somebody seems to pick there. That you see, it has rings everywhere. Of course, we shall not draw the entire thing due to space. If you continue to draw, you will draw and draw. But keep in mind that it only has what? It has rings and layers. That means it has rings. Now, if you look at that, that means now there will be rings everywhere here. You continue them. See, then there will be another layer down here. Yeah, we do not need to show everything, but just show some of you to just mean what we want. So it must be a hexagon. See, it must be hexagons. So yeah, that is the ring, the layered structure of, yeah. Now when you observe this, you see that each carbon here, do you see this? Each carbon here is made of, is surrounded by how many bonds? But remember, carbon had how many electrons out? That means it has only used up 3, leaving 1. The one that has been left will keep moving from one carbon to another, because there will be many. This carbon will give 1, the other one, then they will keep moving. They will be mobile, see? Now, this structure is linked to this other structure by weak forces. See? By weak forces. By weak what? Forces. Yeah. So, of course, when it's like the layers are like this. One layer, there are many rings like this, rings everywhere on one layer. Then layers are like this, but there is no a bigger space that we have put here. For us, we have put in the structure to show, but the layers are just in contact to each other, but we want to show these forces, which are weak forces, and those weak forces were named after a man called Van der Waal. Therefore, they are called Van der Waal forces, or we simply call them weak what? Forces. Van der Waal forces. Now, what's the name of this one? That line, a bond, and its name is specially called the covalent what? Bond. Van der Waals forces. They were named after a man called Van der Waals. See? Now they are so weak that the layers keep sliding over each. Now you see in a structure, whenever you touch a substance and it is slippery, that means the layers are sliding over each other. Like when you touch clay with water, the molecules keep moving against each. But you can't see, of course, with naked eye. You say the molecule cannot be seen. Those atoms aren't what? You can't see them sliding. Oil is very, very silly because the molecules keep sliding over each. See? Now, that means graphite is very, very slippery. Why do you the layers keep sliding over each other? That means in the description of the structure of graphite, we say, that means if I ask you to narrate a story on the structure, you would say graphite consists of a hexagonal layered structure. Then you proceed to say, in each layer there are hexagonal rings. Each ring, you see, consists of a carbon atom joined to other 3 carbon atoms, leaving 1 electron unused in bonding, so making it easier for graphite to conduct electricity. The layers are joined to other layers. There are many layers down. There are many are joined to other layers by weak forces, therefore making diamond smooth and slippery. See, and slippery. Sorry, and slippery. Yeah. I hope you pick that. That is, if I ask you to write about the structure of diamond graphite, can you? You can. See. Let us look at the uses now of diamond. What graphite rather? What are some of those uses?
It's used to make conductors.
Used to make conductors like what? Electrons. See, what else? If it is slippery, what will it help us? What will it help us? Used to make pencil leads. See? That inside part of the pencil leads. So pencil leads. Hope that spelling you'll check it on internet. Is it L-I-D or L-E-E-E-A-D? Somebody check it on Google. That pencil leads, that tip inside of the pencil. If you touch very smooth, see, that means when you get that pencil lead, assuming you have a socket on the house, then you remove some, you draw a line using a pencil, then you get connecting electric wires, you connect to that. See. or just one wire from a socket, connect there and touch here. What does it mean? What does it mean? Will you be shocked? That means you'll be shocked. So, okay, what of lubricating machines? Because it is slippery, not so. Therefore, you can use it to prevent rusting, not so. Because it acts like like what? Like oil. See, amorphous carbon. You look for more uses on internet. Amorphous carbon. We say this is non-crystalline form of carbon, and it means non-crystalline means it has no shape. Now we said we have very many wood charcoal. How is charcoal made? Those who have ever been in the villages, we are going to discuss wood charcoal, how wood charcoal is made. See, and its disadvantages on our environment. See, do you have charcoal at home for making, or use gas? Both. So, how is wood charcoal made? By burning wood. How is charcoal actually? Are we in limited what?
Unlimited oxygen.
Can we give you 3 wood? Can you make for us charcoal? Chiraba, can you make charcoal? Now I happened to be in the village where charcoal is made. But charcoal, they just get a good place, flat place, see, and remove grass around it. Then they can get a hollow tree and chop it. See, they begin with large pieces, arrange them properly. Of course, this is not a 3-dimensional. They would put one piece, they arrange very well, then they put others, see, that when they arrange, this is the flat surface. If those who want to make, if you don't have charcoal at home and you have many trees, please make some charcoal. Then they put like this, they arrange pieces of wood, then others are on over the others. They begin with the large pieces down, like this, then like that. After they have made, they call that structure in their vernacular language called tanuru. Tanuru, like. After arranging, they now get some grass. Small pieces are fixed everywhere around, throw in order. They arrange such that air can, because there is not going to be air, but there is space for, I don't know the science inside that, but put grass, they put some grass, then they carry soil, pour soil all over here, like it becomes like a grave. Pour soil. Then they leave a certain part, a small hole where they will put fire from, where they will light from. You see, the use for covering with soil is not to allow air to make the inside part to have little air. That means they burn wood in very limited amount of air. One time when I had thought of burning wood, I got some sticks and I burnt them in open. I got ash. I was wondering, now how would charcoal be made? Then when I visited where charcoal is made, they arrange well, put some grass, put soil. After putting soil, then they put fire. You must keep checking every after a few hours, because when a hole develops, air will enter through there, and when air enters, it will burn that part to ash. See, they keep coming, checking is there hole, because as fire burns, some part keep falling inside, they keep adding more soil. Now after some few days, like 4 to 5 days, they go and remove the soil and it is charcoal, you see. That means you can get a few sticks and demonstrate at your home. You see, this charcoal can make many things. See, yeah, in our projects we can see that we can make a simple refrigerator using charcoal at home, and it makes very, very cold things. See? So therefore you can make some charcoal. That charcoal, wood charcoal, is made by burning wood in a limited amount of oxygen, in a limited amount of air or oxygen. I think I'll demonstrate how you make charcoal. You can make one at home, but keep monitoring the tanur or that structure you have arranged. Yeah. I hope you have understood. Wood charcoal is made by burning wood in limited oxygen. What are advantages of using wood charcoal? What are some of the advantages? And what are disadvantages? You know them. Use this charcoal, don't you? Disadvantages of using wood charcoal. Does it impact on the environment? Yes, Chirabo, take us through. What are the advantages?
You can have like it's cheap.
Cheap?
Yeah.
It's cheap to buy and even make.
Yes.
Yeah, in the village it's made cheaply, very, very cheaply. See? Yeah, and it easily burns to give out heat, energy. You can easily light. That means cheap and cheap to buy and make. See, next one, it is what? It is easy to light. Yes.
And it's also easy to access.
It is easy to access. See, easy to access. See, it was easy, but now these days it is reducing in being accessed because of and becoming a bit expensive because trees are reducing in number. How would you advise the use of charcoal without affecting? How do you sustain the use of charcoal, making and using it? How can we sustain it? Because the population is increasing, trees are reducing, and what shall we use now as fuel at home?
We can use briquettes.
Briquettes?
Yes.
But they are made from?
They are made from these local materials.
Only without some charcoal? Is there some portion of charcoal there?
There is charcoal there.
There is some little charcoal. Oh, that means can be one of using briquettes which use little charcoal. That's great. Now, what are you saying? You are saying we use gas and electricity.
It's expensive. Still expensive, but you can save trees.
We can save trees. Can we boil beans from a gas?
Yes.
Have you ever boiled beans from gas?
No. Beans
take like 4 hours to be fully ready, dry beans.
Those other countries that are not in Rwanda, maybe let me say that American countries,
They are using what?
They are using gas to boil beans.
And electricity.
But this is Africa. They have the money, so please, this is Uganda. And that's why I say that because that's also people, right?
That means we should use the gas, use electricity, use briquettes. What of the poor people in the village
So they can
who
use
don't have
briquettes.
electricity and gas?
They can use a briquette.
They use briquettes. See, I would advise us to use charcoal without any much effect on the environment. That means you do, why you can't tree? You would tell me that you cut trees, you plant more, not so? But these days in our country, people cut trees without, but make sure you plant at least a tree at home, not so? Yeah. Okay. Now, advantages, we've seen them. Disadvantages of using wood charcoal? Yes?
It leads to deforestation.
It increases deforestation, hence affecting the climate.
Yes, global warming.
It leads to global warming. Why? How?
Trees are cut down, which would have reduced the carbon dioxide in the atmosphere.
That means the carbon dioxide being produced even during burning, okay, leads to global warming due to a greenhouse gas called what? Carbon dioxide. See, what are some of the uses of charcoal? Do you think there are any? Yes, fuel, or not so? Fuel. What else do they use charcoal? So, okay. We can add you more, you'll go on the internet, not so, yes?
Okay, it's kind of a funny answer, but it's
yes, which funny answer is that?
okay. Sometimes people use charcoal like on cultural festivals for decorating their houses.
That's why the answer is funny. For decorating the faces, not so. On cultural faith, it is true. But shall we accept it? Now you research this one. How does charcoal make? That one we can add it. It's true. It's true. Yeah. I want you to go and read how charcoal is used to make gas masks on internet. Then how is charcoal used to in what? In water filtration.
Oh yeah. Teacher, charcoal can be eaten when we're
That means can act as a simple stomach relief.
Yeah.
Yeah. Yes?
Charcoal can also be used in artworks.
Artwork, yeah. Artworks. Yeah. Artworks. Let us look at animal charcoal. Animal charcoal. Then I'll ask you to go and read about coal. Yeah. Animal charcoal. Animal charcoal is made, now any charcoal is made by burning things in absence of air. When they burn animal materials, so like bones, so they will make animal charcoal. And you realize that sugar factories use animal charcoal. When sugar is made, it has that darker brown color. And it is after adding animal charcoal that it absorbs that color from sugar, making it a bit more white. See, that means animal charcoal will be used in what? Removing that darker brown coloring from what? Sugar. So even when they burn you in limited oxygen, maybe myself, a human being, they also get what we call animal charcoal. See, yeah. Now, let us candidates under allotropy of, students under allotropy of carbon. We have exhausted them. Lamp soot. Me, I want you to read about coal. a lamp soot, or we call it lamp black, is got by burning what? Petroleum oils of fuel. Like you burn paraffin, not so? You burn petrol. Yes?
So soot can also be got from a burning candle.
A burning candle, yeah. Burning candle. See? Yeah. Now, listen, we are going to see that indeed the soot is now what? What is soot now?
Soot is the black coloring.
What is that element that makes soot? That means whenever you burn a substance and you get a black material, see, that means you have burnt a carbon containing compound. And I will send you at home to go and burn sugar. In fact, here in the laboratory, we can use a crucible to burn some of these, like glucose, see, cassava flour. See, when we burn them, see, we get the substance will finally become black. See, now listen. Let me ask a question. If we burn, this is called a crucible, where we burn a substance. Of course, we burn it supported on a retort. On a tripod what? Tripod stand, burn, look at the final color. But at home you can definitely use what? See, a small saucepan. Let me ask a question. We have said if you burnt material, rubbish at home, and you saw black smoke, what are you seeing? Exactly. That means black particles produced in smoke is just unburnt carbon that was in the structure of the material. Now, students, I want to ask a question. If we burnt carbon itself, of course we have said that every natural material on earth has what? Carbon. And that's why the name organic is given to them. See? Now, carbon, if we burn carbon alone, see, it is a chemical change that produces, listen, soot plus what? Oxygen, or any form of carbon, like charcoal, plus oxygen. See, charcoal plus oxygen. This is a chemical change because you are applying what? Heat. See, you must produce a new substance called what? Carbon dioxide. See, carbon dioxide. Now listen, that when you have enough air, listen. Now, when you have enough air, I'm dropping to fuels now. You see me turning slowly the bearing from soot. I'm now rewinding into fuels. See? Turning into fuels slowly. Now, This is going to throw me into fuels. When you burn carbon, charcoal, whatever, listen, you get what? Because carbon is mixing with oxygen to form a compound called carbon dioxide. See, carbon dioxide. Yeah. Okay, now look here. If we burn salt to get carbon dioxide, this occurs when you are burning in an exposed place where there is plenty of oxygen. But when you burn in a little limited oxygen, you don't get, instead you get carbon monoxide. See, very, very poisonous gas. And what does it do? You see, it is very poisonous when you cook in a closed house. There is little air inside, and you'll be producing carbon monoxide. Therefore, when you are cooking, ensure you open the doors, even if you are using gas. See, because you'll generate carbon monoxide, which will enter you through respiration and go into your blood, make it unable to transport oxygen. That's why you hear people, when they take your oxygen, you are energyless, because oxygen is used to facilitate what we call the metabolic activities that give energy in your body. When you inhale carbon monoxide, blood won't transport oxygen, because it will have reacted with carbon monoxide and formed something else that makes blood unable to transport oxygen, and the effect is irreversible. You just have to die. See, just have to die. Unless you are rushed the same minute to the hospital, which can't happen. Because when you are inhaling that gas, you won't know. You just wait for death in the house, not so? Yeah. That means never burn any fuel in the house in limited oxygen. Turning now to fuels here. Fuels. Lamp soot, sorry, we have left out lamp soot. There is used in what? Now I'll send you to a project. You research how we make shoe polish. How shoe polish is made locally at home. See, now we are seeing that lamp soot can make shoe polish. See, can use to make black ink. See, black carbon paper, the ones you see used in writing receipts. Now turning to fuel. A fuel now. See, that's where you see chemistry is very interesting. See, very, very interesting. What is a fuel? Now, okay, let us see. Under fuels, we are going to see what's a fuel. So many things here. Then the chemical nature of most fuels. What is the element that makes up fuels? Chemical nature of fuels. See, fuels. Sources of fuels. See, sources of fuels. So then you look at the fossil-based fuels. Fossil. Fuels from fossil material. fossil-based fuels. See, then you see this part is quite wide and interesting. See, effects of burning fossil what? Fuels. Then that one will throw us to what we call global warming and greenhouse effect. That means I will ask you to remind us of that material when we saw under air pollution. Greenhouse effect. See? Yeah. See? Now, what is a fuel class? You have interacted with that word for long. What is a fuel? Yeah, Chirabo, you are thinking?
A fuel is anything that can be burned to produce heat.
Period. To produce energy or heat energy. You see, fuel can be used in vehicles to produce energy, not so? It is a substance which, when burnt, produces heat energy. Produces heat energy. Yeah. Now, chemical nature of these fuels. What really is in the fuel that is burnt to produce energy? Yeah, as a chemist, you must know chemical nature of fuels. What is found in those things? See? Yeah. Chirago, from our discussions, what is found in the fuels? Which element there? Carbon. That most fuels contain an element called carbon. And why do we use those carbon-based fuels? Is that carbon has a high calorific value. Why carbon-based fuels are used? Because carbon has a high calorific. Now, internet will tell you that the calorific value is just the amount of heat a substance can produce when burnt. That means carbon can produce a lot of heat. Yeah, calorific value of a fuel. The calorific value of a fuel is the amount of heat produced when a fuel has been is burnt. Let us see sources of fuels. Sources of fuels. Now wait. Before you see sources of fuel, there is something here. You told me that most fuels is carbon. How can we show that? How can we show that most fuels that are burnt is carbon? How?
Because when they are burnt, soot forms.
Say it again.
Because when they are burnt, soot is formed.
Soot is formed.
Yeah.
Soot is formed. Do you agree with that answer? What is the final residue left behind?
Ash.
If you burn a sugar cane. Ash. See, that burning and you attain a soot, that black smoke, shows that there are particles of carbon that are being produced and are left unburnt. Because you see, fuel is burnt to produce soot. Does a fuel going to produce soot?
Yep.
Soot is carbon. There are also other things. Carbon dioxide, not so? Carbon dioxide. But we are going to see that the fossil fuels produce, for them they have carbon and hydrogen. They have two elements here and the other elements like sulfur. That's why for them, instead of producing only carbon dioxide, salt, they will go ahead to give us many things. Sulfur dioxide, see, carbon dioxide, you see, salt, and they will be very, very dangerous here because they would really cause many pollutant gases to be produced. Now, sources of fuels here, sources of fuels. On Earth we have what we call renewable sources and non-renewable. What does that word mean, to be renewable?
Can be replaced.
Can it be replaced? To renew is to replace back. Let us start with renewable sources. See, yeah, is wood a renewable source or no? Are you sure you can't replace wood? Are you sure? You can't use wood again?
If you burn it to ash, you won't use it again.
See, isn't wood renewable? What of water? So,
Okay. Looking at the other side, I think wood is renewable because you can plant trees, burn again, just have a say.
you burn as you replace.
Yes.
It means you can't deplete. Okay, let us proceed here. Renewable sources are those sources which can be replenished or reused again. Replenished or reused again. Replenished or reused again. They include what? Yeah. Okay, we can first also give non-renewable sources are those sources which cannot be reused or replenished. Then you can outline for me examples. That means I'm going to give you a table. You go to Google. So, examples of renewable and what? Renewable and renewable sources. Renewable sources give us renewable fuels. Non-renewable sources give us non-renewable fuels. Non-renewable sources. You are going to give me many. Me I've only given you one as water here. Water can be replaced. Here I've given you what? Minerals, not fossil based fuels. That means we can just see we are mentioning them as what? Sources. What is not a fuel, but just an echo. Maybe we would be specific on sources that give fuels, not so? Yes. Yeah. Sources that give fuels. Under here we shall put it because we shall have coal there. Minerals like what? We shall include the minerals because we can access coal underground. See, Yeah. Yes, petroleum, oils, natural gas. Yes. I want you to go on Google. So. Now, the patient is saying that renewable are not there. No. On earth, you can't say you have it, this and its opposite is not there. See? Hydroelectricity, is it non-renewable? It's from water. It's from water. That means that energy for cooking is renewable. There is what we call a geothermal energy. Geothermal source of energy. This is used by science. This is the heat that the earth gives. Got from the earth itself. See? Cow dung is renewable.
Like biogas.
Yes, cow dung. See, but you were telling us that they are not there. You see, see, that's right. Yeah. Now we are starting. Let us pick out to call the fossil-based fuels. They are the ones we get from here. Petroleum oils. Now, could we rub off this?
Yes.
Fossil-based fuels, then we shall see effects of burning them. Yeah, fossil-based. You'll add more from Google, not so?
Yes.
Fossil-based fuels. Now, these are fuels that are got from fossil materials. Now, let me give you this history. You see, Uganda is said to have oil. When they say oil, they don't mean cooking oil, no? They mean petroleum oil that can made broken, can be distilled to give us petrol, diesel, see, gas for cooking, see. Now, Uganda has petroleum oil, clear? Now, the petroleum oil was formed very many years ago from decayed plants and materials. Now scientists estimate that this petrol that is down in Uganda started to be formed between 300 to 400 million years back. You see, science is a bit, you might say, I think Christians, you are not saying science is against you, not so? Somebody saying science is against you. See, now we would think that these creatures existed because science says between 300 to 400 years back, 400 million moreover. But you find out that one. We shall not go into science and religion. But for us, we are saying that science speaks this, not so? Yeah, between 300 to 400 million years back. That how was it formed? How is this fossil-based fuels, and we said they include petroleum oils and what? Natural gas. Natural gas, I think, let me, before I give you that history of how petrol was formed way back there, petroleum oil produces many products. Like petroleum oil is a source of petrol that you see, diesel, not so? Diesel, paraffin, which is called kerosene. Then we have natural gas, the gas used for cooking home there. At home we have a gas called butane. See, butane. Even these oils also give us, they give us what we call, it gives us gases, cooking gases. These ones also give us gases, please. Even there is natural gas that came naturally. See. And the major part of natural gas is called what? It's called methane. But other natural gases are there which are in very little quantities called ethane, propane. But at home, see, at home there, we use basically what? Butane in our gas, like the one we have here is having butane. See, butane. That's right. That's right. Now, how were these ones formed? Science says these fossil-based fuels were formed between 300 to 400 years ago. See, and they were formed as a result of plants and some animals. They believe that there existed some animals called dinosaurs. Dinosaurs. Some you look for that name. How those animals plus plants that were there a long time decayed. When they decayed, they were covered by layers of sand. That when you decay, nobody buried you, therefore sand came and buried you. See? When sand buried them, the earth has a lot of heat in itself. That heat in the earth plus a lot of pressure from the sun converted those decaying materials into petroleum and natural. See, that is the oil in Uganda was formed 300, 400 million years back. See, I don't know. Now that is true. Now, let us look at effects of burning fossil fuels here. What is the effect of burning fossil fuels? Now listen. The chemical nature of a fossil fuel is not only carbon. It is made of, see. Now listen, we have said a fossil fuel has carbon and other elements like sulfur and hydrogen. See, that means when you burn a fossil fuel, you are going to get carbon dioxide, you will also get carbon monoxide, you also get water vapor. See, sulfur dioxide. Why do you think you get water vapor? Yes, Chirabo.
I think because the substance will contain both hydrogen and oxygen.
Because it's having water in them? You are very, very sure. Okay.
Well, when you see cold, it's like as if it's watery, so it stops it.
Okay. Okay. That's pretty good. See, you said why do they produce water?
Because they contain both the hydrogen and oxygen atoms.
Then, pencil, why do they produce water? They have some water in them. That's why they produce water.
No, water vapor. Steam. You can't produce steam when you don't have water.
Oh. Now, me, I will pose a question. How is steam formed?
From burning water that evaporates into the atmosphere.
Here I can see that reasoning. See. Now, assuming you form water, what makes you to form water?
No. Yes, the hydrogen and oxygen. No, like from those things we're studying right now.
That's very, very tricky. Some are saying a fossil fuel will burn to produce water because it has water already. Another one is saying it burns to form water because it has hydrogen and then what if you burn hydrogen alone in oxygen? You get? What do you get? Hydrogen oxide is called another name? Water. See, hydrogen oxide is water. You see? Now we are saying a fossil fuel has carbon, has sulfur, has hydrogen. Carbon will change into carbon dioxide and carbon monoxide in case. Now listen, that fossil fuel has carbon, therefore carbon gives carbon dioxide, and the carbon monoxide we have said is only formed in a special time when what?
When they are burning carbon and
limited oxygen. That's why, listen, that's why petrol in a car is burnt in limited supply of oxygen in a closed engine chamber. Did you know that energy that to drive a car is as a result of burning in a combustion chamber of the engine? See? Have you ever thought of how that car carries you and the energy it gets from where? You see? It's just the engine has a special chamber where petrol burns. When it burns, it expands a certain device called a piston. See, now it's burning in a closed part under limited oxygen, therefore it's producing carbon monoxide. That's why we don't advise children to follow the cars smelling the exhaust pipe, because it smells well, not so? The cars waste fumes smell nice to some, not so? And they follow smelling. Please don't, because you will die. See, it produces carbon monoxide inside there. If it happens that by the time the carbon monoxide leaves the engine and it has not been converted to carbon dioxide as it goes out, then you will die. See, so you will die. See, now we have seen that. Then it has sulfur that produces some gas called sulfur dioxide. Sulfur dioxide is acidic gas. Acidic. It also has hydrogen that liberates production of what? Water. Now why water is formed is because there is hydrogen that burns in oxygen to give us water. Okay, fine. Effects of burning fossil fuels. Let us look at them. What are some of the effects of burning these fossil fuels? Effects of burning fossil fuels. Now let us try to hurry because things are many to exhaust. See, heat is formed. Okay. Effects of burning fossil fuels: production of heat. Heat for fuel, not so? Yes, heat for fuel. What else? Soot and smoke. Huh? That means when you are using, you can, soot is That means you can even darten your saucepan, not so?
Yeah. Like that, you get energy, respiration.
Okay. What else? What else? Yes.
Increasing carbon dioxide in the atmosphere.
That means you are talking about directly a greenhouse what?
Greenhouse effect.
Yeah, yeah. A greenhouse effect is just the effect caused by those class of gases called greenhouse gases. So, and now that one works together with what we call a global warming. See, oh, now it is throwing us. That means, oh, you didn't talk about air pollution, which results into things like acidic rain. Because these gases are acidic that come out like sulfur dioxide. Therefore, the rain that will come will be acidic, will affect your skin, see, will damage buildings. See. Yeah. Now let us turn very fast to global warming and greenhouse effect. Global warming and greenhouse effect. Now listen, we gave a history of the word greenhouse effect under when we covered what? Air pollution, global warming. Now who recalls what did we say this greenhouse effect meant? Because it is a term that was first used by one of the scientists a very long time ago, and it is now being used these days. See, when certain animals, certain plants which were weak, couldn't stand strong sunlight, were always grown in some special houses which have transparent roofs. See, those transparent roofs, those days, to be transparent was permit sun's rays to what? To enter, not to be exposed to strong source of light, source of sunlight. Therefore, those weak plants which couldn't stand strong light were put in special houses, because every plant needs light, but some don't need very strong one. Therefore, those houses that kept those weak green plants were called greenhouses, and that's where the term started from. They are used to receive sun's rays slowly, and the sun's rays, when they reach here, is not allowed to go out. Now, the heat coming inside in that room there is supplying warmth to the plants, and that supply of warmth is what we are calling greenhouse effect. Now, that term was just borrowed to be used here on Earth here. See, that on Earth here, there are some gases called greenhouse gases in the atmosphere. See, now, greenhouse effect is an effect that results into heating. Up of the Earth due to greenhouse gases. And the heating up of the Earth is called global warming. Now, the greenhouse gases included the carbon dioxide was one of them. There is even water vapor. Water is a poor conductor of heat. See, poor conductor of heat. Therefore, when it absorbs heat, can't easily leave it. There is nitrous oxide, the compound from fluorocarbons, compounds having chlorine and fluorine. See, You see, many plastics these days are made of chlorofluorocarbon elements. Therefore, burning plastics is very, very dangerous. See, because of it contains chlorofluorocarbons, which also being used as greenhouse. There is also a scientific study that even refrigerators also they use their chlorofluorocarbons. Therefore, they are doubting that the use of refrigerators at home is not good because of the chlorofluorocarbons, which are cheap. They are cheap, and therefore they can make materials at a cheap cost. Now these gases, listen, let us summarize this part here. These gases here, when sun is even ozone is just listen, ozone occurs in the second layer of the earth of the atmosphere called the stratosphere. Yeah, remember we are in the troposphere now. The second layer after troposphere is the stratosphere, and it contains a region of air, a region of a special gas called what? Ozone. Ozone is not a blanket, it's just air that is existing in a certain region called the stratosphere. And that layer, ozone is a molecule having 3 oxygen atoms. Ozone is like this. See, it's just gas molecules which have the capacity to trap dangerous light rays called the ultraviolet rays from the sun. See, now industries are spoiling it, and that region is being destroyed by chlorofluorocarbons. It means when your country has a lot of cars burning petrol, you will be suffering ozone layer depletion of that special layer of gases that traps those air. Now when the sun reaches the earth, see, these gases, when there are so many on earth, remember air is a poor conductor of heat and water. Therefore, they will trap heat in them and not release it. Therefore, since the atmosphere will have trapped heat by this, the earth will warm up. That's what we call a global warming. The warming up of the earth's surface due to greenhouse effect. So, carbon cycle. Next is the carbon cycle. See, carbon cycle. Yeah, carbon cycle. You can research more on internet to study about greenhouse effect and global warming. Now, can somebody carbon dioxide in atmosphere? Let me draw a simple cycle here for you to help me. Animals. Fossil fuels, petroleum, oil, natural gas, plants. See, now if we can look at this, I think I should shift animals a bit aside here so that we can see animals. How animals? Now we've seen that how are they connected? Who takes what? Who eats what? Remember, did we say that all of plants and animals is carbon?
Yes.
See. Now what makes you to decay? What I will not say you. What makes things to decay and become soil again?
Bacteria.
Why can't a cavera decay? So
Because it's not natural.
it's not natural. It's not natural. Okay, let us discuss this because of time. Let us discuss this because of time. How, who eats who, and to produce who produces who, and which process. See? How is the carbon taken to the other form or taken to the other thing? Who takes the carbon to the other, who eats carbon in terms of the other? Yes, Chirabo?
It starts from the animals.
Animals, they do what?
They'll eat plants. Okay, no. It's this girl's idea, not mine. But my idea is...
Yes, let me put them in.
The animals will die and decay. They'll be buried by soil, yeah?
Animals, they decay.
And they'll form that fossil, those fossils.
This is decay and what? Death and decay, not so? Yeah. Okay, that's very, very great. Death and decay.
Animals eat plants.
Animal, this is feeding, not so? Feeding.
Animals produce cow dung.
Animals produce cow dung. That one will be what? Here?
Yeah.
That's still decay.
Even animals can gas.
Can gas carbon dioxide? What? That is the one here. What is that? What process is that?
Expression.
Exi? You are gassing. Now let us see. You see, when you produce a gas from the what? When a human being produces a gas from where? You see. Now, the gas you produce from behind the exhaust pipe of a human being is not carbon dioxide, you know. Carbon dioxide is odorless. See, that means you do research. So, it's odorless. Now this is respire. They respire. See, they respire. Out of here also, respiration. Why? How could this go here?
Even
When those fossil fuels are burned.
even carbon dioxide to plants.
By?
When plants take it.
Hey, this one is called?
Photosynthesis.
This is called photosynthesis. Great. Photosynthesis. That's very great. Now, what of this? How is this attained? This is combustion. Yeah. Combustion. That's very great.
But teacher, isn't it also possible that plants give out carbon dioxide like when they are undergoing germination?
Yeah, it happens. They do. They do. Those are many other processes. Germination, not so? Yeah. Germination.
When you're burning fossil fuel.
This one here. Okay. Now, could we now say how to increase carbon dioxide in the atmosphere? How do you do that? How to increase amount of carbon dioxide in the atmosphere? How does it happen? Yes, how does that happen?
Burning fossil fuels.
That means burning fossil fuels.
Decaying plants.
Decay.
Respiration.
Respiration, does decay respiration of plants, not so?
But
And animals.
something is decaying. Is that smell? Like when something is decaying, produces fumes and smells. Is there also carbon dioxide?
There is a possibility. It's very, very possible. In fact, this animal to carbon dioxide here can be also through death and decay. Can happen. Can happen. Okay. Now here respiration, photosynthesis, germination. Are many here. Death and decay. Okay. How do you reduce carbon dioxide in the atmosphere? Photosynthesis.
Reforestation and afforestation.
Reforestation and afforestation. But the process is they all take it by what? Photosynthesis. Okay, I've left that. I'm now on discussing carbon dioxide and its properties. Carbon dioxide and its properties. Yeah, that's a very, very good, very, very good. So, yeah, now it is a long topic, but you need to be very attentive. Now let us go to carbon dioxide and its properties. We shall discuss how do you prepare it locally in the laboratory. Carbon dioxide and its properties. Now when you are writing, it's good to leave space there. Carbon, then dioxide and its properties. Now we can prepare it in the laboratory. That gas is very important to us because we use, you know where it is used. Yeah, laboratory preparation of carbon dioxide gas. Now I'll give a simple we use the requirements here. We just need we need what we call calcium carbonate powder, or any other suitable powder can work. And this one is always called the marble chips or limestone or marble chips. See, we now use dilute hydrochloric acid. See, now I will only demonstrate a simple preparation, but I'm going to ask you to go and research on preparing a dry sample of pure carbon dioxide gas. But I'll just show you that when you mix an acid with this, I think you recall something in acids there, that when you add an acid to a carbonate, you liberate what? You liberate three things. Now, I'm going to ask you to just have a simple demonstration here using a boiling tube, and we shall clamp that boiling tube shall clamp it. Then we shall also have what? We shall also have another a test tube here. But for you, you'll prepare a sophisticated, you'll prepare a dry one. I'm going to illustrate how we prepare a dry one here, but a simple one to prepare in the laboratory is this one. It's prepared from what we do is that we put inside here calcium carbonate powder and an acid called dilute hydrochloric acid. Dilute hydrochloric acid together with marble chips. See, this one is a simple one that we can illustrate here in the laboratory. Lime water, lime water. So lime water. You can use a boiling tube is larger, or test tube. It can also work. Then we have the cork. Now make sure the cork here is it is just like this. That means it is to cover, to make a tight seal on the walls here. That's why it has kind of, you insert it forcefully there. See, then this is our delivery tube, a small glass tube here. Smaller glass tube. Because the time can't permit us some of these experiments, we do them in project work outside the class settings after us learning this. See, that's a simple preparation that we can do in the laboratory. That would mean that would just mean the arrangement is such that we clamp this test tube here, and this one is made to be supported here. But of course it can't stand alone. We can also introduce another retort stand here to clamp it. That means this boiling tube, we first place in the calcium carbonate powder.
Sodium carbonate.
Yes, or any other carbonate that is suitable, or any other carbonate that is suitable. Then that means this is the lime water. It's a colorless liquid. Now lime water is used to test for carbon dioxide gas in the laboratory. Now what actually happens is that these are connected. Lime water is added here a little. Just don't put very little, because if it is much it will need a lot of carbon dioxide. Just very little here, so that carbon dioxide will go there and show a chemical change here. Now this is clamped, and this is supported with another clamp here. Then we connect here a cork. Unfortunately we don't have one here, but a cork is just a small rubber, red always in color, rubber like that. We just bore here a hole inside, and we put a delivery tube. Then we insert that cork inside this pipe, inside this boiling tube here. Then you connect that end of the delivery tube there. Then inside here we first remove the cork, pour in any acid. Pour in any acid here called dilute hydrochloric acid. We first pour dilute hydrochloric acid here and close with the cork very fast here. Then we allow the gas to bubble into lime water here. Now when an acid is added to calcium carbonate or Na carbonate, you are seeing that boiling there is indicating that now you do the process of putting the acid carefully and very fast. It is indicating that carbon dioxide is coming out. When we allow it to enter lime water will turn milky. Lime water will turn milky. Now in improvisation, if we don't have a delivery tube there, we can improvise. We can make an improvisation there for those in case you lack now those who want to do it at home, you can prepare simple carbon dioxide at home from baking powder, the one you bake mandazi, and you prepare, you squeeze a lot of lemon juice, see, and you pour it in the baking powder. It will give you carbon dioxide. Now to allow the gas slowly enter there, we can improvise by a paper. We close a paper on this section and also get our lime water section and close the two. Then as the gas leaves here, it enters here, this will turn milky. It will turn milky. Lime water turns milky on addition of when the carbon dioxide enters it. Yeah, that one we shall do it in project work to prepare that gas, test for it, and that one will do us good. That's good. Yeah, now I will ask you to read the other. If in case you wanted to prepare a pure and dry carbon dioxide gas in the laboratory, we would not use that simple diagram. Of course, we would have a section for all these will be done, because these experiments need a lot of time. But we can demonstrate here. Then in our project work, we can go and do it and even test it. Now what we do, we use a round bottomed flask here. A round because we don't need any heat, round bottomed flask, or use a conical flask. We can use a conical flask also, it can work, or a round bottomed flask. Then we introduce in a thistle funnel, or we use a dropping funnel here. Then we connect to a part that purifies the gas first. We can connect to another test tube or wash bottle. Can use a wash bottle here or a test tube having something there to clean the gas. To clean the gas there. Then we connect. I'll show you. Then I'll ask you in our project time we are going to prepare this gas together. Now we also, since we need a dry gas, we pass through drying agent to dry the gas. We are using these boiling tubes to act as the reagent bottles. Then we collect the gas in what we call a gas jar. A gas jar here. It can stand alone. Now these delivery tubes are not long enough. We normally have we normally connect look here. Now look here. There are some funnels here which have a tap and some don't have a tap. Some have a tap here where we regulate the acid. At this point we add here dilute hydrochloric acid. Dilute hydrochloric acid. Then inside here we put calcium carbonate powder here. Calcium carbonate powder. Then this delivery tube here goes inside here. It hangs at the end of the cork to allow the gas to leave it. Then it is connected to another delivery tube from here. Because the delivery tube is not long enough, we connect using a rubber tubing. This connection is a rubber tubing. Then we connect like that, and we connect this way. Now inside here we put a drying agent like concentrated sulfuric acid to dry the carbon dioxide before it is collected here. Concentrated sulfuric acid to dry the gas. Then here we put water to clean the gas by removing some fumes produced by the acid here. It removes the fumes from the acid, or we can put a solution called potassium hydrogen carbonate. Either put water or this to purify when the gas is produced here, it is purified here, then dried by this, then collected by now that downward method. We are collecting it by downward delivery because we are delivering it downwards there. I will ask you to do more research on this study, but we are going to do it practically. Because of time we cannot prepare it now. But this is a boiling tube. We can use a wash bottle, boiling tube, and cork very well and connect very well. Then we pour here the acid. When we use the one with the tap, the pipe does not this cystophano tube does not go up to the bottom. But in case there is no tap here, we push this up to the bottom because the acid can we have to take it up to the bottom when there is no tap. When there is a tap, we don't. It hangs in space. It hangs in space. Somebody is asking. I think that will be enjoyed when it is an actual practical. Why it is, if you put at the bottom, we shall compare when you don't put at the bottom in the practical. See, but we are saying that you pour the acid here. Now the one with the tap is called a dropping funnel. Then the one without a tap, because this one is used to just drop the acid regulatively, dropping funnel. Then the one which we have without a tap, we call it cystophano. We are going to prepare it in the laboratory. Here we receive our sample of dry carbon dioxide. It will be very interesting to see how we prepare that gas when we have ample time, because we need to set those apparatus here, there. See. Yeah, as I think you see, we want to discuss now how do you test for carbon dioxide gas. We have seen that we test it using which solution? we test using lime water. We test it using lime water. See, now we saw that most fossil fuels can produce carbon dioxide. Therefore, the way to check that a fossil fuel produces carbon dioxide is to burn the fuel and connect it to a supply of lime to where lime water is. See, to where lime water is. Yeah. As you observe, I want to shift very, very fast to how do you chemical test for carbon dioxide gas. We have said chemically using lime water. And how does the color change when carbon dioxide enters lime water? The gas turns, the lime water turns milky. The lime water turns milky. So the lime water turns milky. Yeah, turns milky. Now as we finish up, we want to start on, I think we have captured the chemical test. You bubble the gas through lime water and it turns milky. See, it turns milky. See, this is called a dropping funnel. We said when it's a dropping funnel, it hangs. See, when it is a thistle funnel, it goes up to the what? Up to the bottom. But you do, why would you think so? Patience, you asked. See, why should this one hang and a thistle? A thistle we mean when it has no top like this, we push it until it goes into the solution here. And remember, see, every pipe that brings the gas into water for purification must enter water. Then the one where the gas leaves must be off the water to allow the gas to go and that one would be seen. I wanted to see it. You are persisting why, but you can see why is this one necessary to go. When it hangs, what will happen? See, remember there is the gas is bubbling, coming out. That means the gas will, if it hangs here, there is no closure here. The gas will what? Will try to come. See? But when there is a tap, there is a closure. See, even if it hangs, no problem. So, shifting to physical properties of that gas. This one we shall do it practically, but you can go on YouTube and enjoy that video for preparing carbon dioxide gas. See, a dry one and a pure one. Remember, water was for purifying, and sulfuric acid, which is concentrated, is for drying it. See. Physical properties of carbon dioxide gas. Which obvious one did we say?
It's colorless.
It is colorless. Yes, colorless. Odorless. It has no smell, to be odorless. You see that we collect it downwards. That means we can't collect it upwards. Why? Why can't you be able to carry somebody in the air but you put him down?
Because it evaporates easily.
See? Are you sure? Evaporates easily? But that word chemically true. A gas evaporates. See?
Okay, goes.
It diffuses easily. Okay. But let me ask you, can you carry a heavy jerry can on the head and sit with it for the whole day? Why can't you sit with a jerry can of water on the head?
Because the longer it stays there, the heavier it becomes.
It is heavy. That means something that is heavier than air cannot stay in air up, but it stays down. We say carbon dioxide is denser than air. That's why it is preferred in fire extinguishing, because it will stay on the earth's surface. It want to go in the air to leave the fire point. When you put it on the fire point, in fact it will just want to sit on the fire because it's denser than air. See? Yeah, now how do you know, see, that carbon dioxide is denser than air? This can be a practical experiment at home. Please go and try it. Clear? Go and get a cup or a glass. Then pour there baking powder. Clear? Get a matchbox, put a matchstick. Put it, one should be a little inside, another one should go many meters down, another one should be just here. Then get lemon juice or vinegar. You can buy vinegar from a shop. Get vinegar. Pour here, or any acid, if you have an acid at home. Pour here, but put light each here, light each matchstick here, and pour. See, when you pour, you here. This is baking what? Baking powder is sodium hydrogen carbonate, as we saw in what? Under acids is sodium hydrogen carbonate. You pour there lemon juice, a lot of it, lemon juice, but here there is a flame. You will lit these things. See? Now what will happen when you pour there lemon juice? It will react with the powder to you will see bubbling, you will see this thing kind of producing bubbles, and that will be carbon dioxide gas. You realize that this matchstick will die off faster than the rest. This will be last to die off because carbon dioxide will prefer sitting, it can't prefer going up because it is heavy. It prefers settling down. That means by demonstrating that this matchstick goes off fast, carbon dioxide is more at this lower level than up here. See, than up there. Now let us look at some of the, that means it's colorless and odorless, denser than air, diffuses easily because it's a gas. See, now we said that gas is acidic, meaning when you allow it to enter water, water will become acidic. That means when you bubble carbon dioxide in water and test water with litmus paper, what will happen to the litmus paper?
Red litmus paper.
Blue? Red litmus will turn blue? Is it true, Chirabo? Now we're checking the head in refusal.
If it's an acid, then you should use a blue litmus.
And it will turn red. Red remains red, blue turns red. See? Yeah, that means carbon dioxide turns blue litmus paper red. Yeah, that means it is an acidic what? An acidic gas. Okay, let us see some of the chemical properties of carbon dioxide, and we shall now shift here. Of carbon dioxide gas, we have said it reacts with water to form an acidic solution called the carbonic acid. Have you heard the first chemical property? It reacts with the water to form an acidic solution called the carbonic acid, which turns which turns blue litmus paper to red. Turns blue litmus paper to red. Did it react with lime water? Yes. Now lime water is Kalisha, the other chemical name. Here it reacts with water. Reacts with water to produce what? To produce carbonic what? Carbonic acid. Then it reacts with lime water to produce a milky solution. Lime water is colorless, it turns milky. The milky solution is called the calcium. The solution turns milky and it's called the calcium carbonate. We shall not call it a milky solution, but milky substance called the calcium carbonate. Have we said that lime water is also called the calcium hydroxide solution? The other chemical name is calcium hydroxide solution. Yeah, I'll ask you to go and research on how carbon dioxide reacts with magnesium metal. That means do some research here. How does carbon dioxide chemically react with magnesium metal and sodium hydroxide solution? Yeah, and sodium hydroxide solution. Now there, we shall not exhaust a lot there. You'll do some more research there. For us, we are now going to uses of carbon dioxide gas. Where is carbon dioxide gas used? Where is carbon dioxide gas used? Yes, Chirabo.
It can be used by plants for the process of photosynthesis.
Yes, used in plants for photosynthesis, right?
It's just to take out the fire.
Yes, as a fire, used in fire extinguishers. Used in fire extinguishers. I remember we mentioned some under air. Do you remember some more? Under air. Which juice do you take that has carbon dioxide? That it's used to make fizzy drinks, like soda, fizzy drinks, like soda. Yeah. Yeah, we shall see many others making baking soda. Yeah, but you add, you have more? Preservation of drinks. Couldn't we say the same point in fisher drinks? Yeah. Used in preservation of drinks, like the fisher drinks we talked about. Okay. We shall not overdwell there, but we shall now go very fast to hard water and soft water in details, and soft water in details. We shall look at methods. How do we compare hardness of water? See, somebody remind us, hard water and soft water.
Hard water is the type of water that does not form lather easily.
Hard water is the type of water that does not form lather easily.
The soft water is the type of water that forms
lather is easily. Yeah. Now let me ask. That one is throwing us to types of hard what? Hard water. There is some hard water that when you boil, if it was not giving leather, it will start giving leather. See, there is another one which when you boil, if it was giving leather, if it was not giving leather, it will not give leather. That means some water can be softened by boiling, some might not be softened by boiling. See, by boiling. Now, let me first emphasize this point before we can move on to the types. You see, water from the atmosphere, what really makes water hard is that you see, you cannot behave in a certain way unless there is a problem with you or something unique with you. Hard water is different from soft water in that, say, that means, let me first have this highlighted here to guide us, difference between hard and what? Between hard and soft water. You gave me that. Then two, what causes hardness in water? 3, sources of hard and soft water. See, then types of hard water. Then we shall also see types of hard water, methods of removing hardness in water. Then lastly, uses of hard water. Yeah. If we can exhaust that, then that will be the end. So now I request that now you pay maximum attention. Most of these things we can visit them. You see, life is now easier for us. Internet has made life so easy. So easy. Just type in hard water sources, you'll see them. Now let me explain this. When water is from rain, before it touches the ground, there is no dot of a mineral salt in it. You see, when we talk about a salt, you understand. I mean compounds like calcium sulfate, compounds, see, that we talked about in salts there. We don't mean certain other things. But now we are saying that when water has not touched the earth's crust or surface, see, it can't be hard. Now, water that comes to our homes, see, some comes from mountains, some from lakes, some from rivers. Now when water touches the earth's crust, it mixes with mineral salts that make it hard. And not every mineral salt makes water hard, you know. Water is made hard by the presence of salts of certain elements, which is calcium or magnesium. That the mineral salts of calcium and magnesium are responsible when water mixes with magnesium salts like magnesium sulfate and calcium sulfate, or magnesium hydrogen carbonate and calcium hydrogen carbonate. Those special salts make water hard. That means difference between hard and soft. You told me water does not make leather easily while washing with soap, while soft water makes leather easily with soap. Now we dropped here what causes hardness in water. We have seen that it is caused by, yes, the mineral salts containing magnesium and calcium, see, that are found in the earth's crust. See, yeah. Now, sources of hard water and soft. There it means you can tell me.
Rain is a source of water.
That means hard water and soft water. See, our patients have told us that soft water is from rain. See, which other water can be soft? See, sea is in the ground, in the earth. Sea is within the earth, not so? In the laboratory, which type of water is soft? See, that we make for us ourselves.
That contains washing soda.
Yeah, the one that contains washing soda. But there is water that we can make there called what? We can get normal water and distill it by simple distillation, and we leave behind all the salts so that what we evaporate is pure water. What is this? Hard water is got from? You give us the first one also. Springs, taps, wells, you know, sir? Oceans, lakes, rivers, mountains. Now you see that some contain few salts and might not show a lot of difficulty. Did you realize that when you are washing with rainwater, leather forms so fast? Yeah. But this, not in comparison to tap water, these ones form leather much slower, but they form because they will have few salts. Let us look at types of hard water now. permanent hard water and temporary hard water. Thank you very, very much. Permanent hard water and temporary hard water. See, permanent. Now I will put here both types and we discuss them. See, types of hard water. We have permanent hard water and what? Temporary. Who was researched? Yes, I can say hand there. Patience, you have researched. Talk about one of them. Patience.
Temporary hard water. Its hardness can be removed by boiling.
Boiling. Temporarily, you just boil and it becomes soft.
But permanent hard water, even though you boil, even though you add washing soda, it won't.
It won't. So, do you have an alternative, Chirabo?
It was the same.
They say that this is the water that cannot be made soft by boiling, not so? While temporary hard water is the water that can be made soft by just boiling. Now you research here, what are the chemical substances that make water permanently hard? And what are those that make it temporarily hard, that when you boil it softens? Those who have done, you know, you've done some research.
Adding salt.
Adding salt. See, let us be with salt, because there are many salts. See, now the and calcium. Now the salt here is calcium sulfate, or any of these that is in the water makes it what? Permanently hard. You see, even if you are permanently hard, in the laboratory we can make you so soft. See, but boiling, the only difference is that you can't boil and it softens. See, now this is caused by calcium. I hope you can write for me the chemical formula of calcium sulfate. Then calcium hydrogen carbonate and or magnesium hydrogen carbonate. Yeah, again carbonate. These are the ones that make water temporarily hard. Yeah. Yeah, now let us discuss the methods of removing hardness from water. Yeah. Methods of removing hardness from water. Wait a little bit here. I think this is captured very well. See, now, I don't want to fast rub this. I want to say something here. You see, this calcium hydrogen carbonate and calcium hydrogen sulfate, when you boil any of them, when you boil, heat will break it, it changes to calcium carbonate. And this calcium carbonate, we are going to call it a special, we are going to call it a special, let me capture something here first. Before you capture that chemical word, let me turn here first. See, look here, let me have this methods of removing hardness from water. Listen very attentively. From water. Now I will start by removing temporary hardness. Removing temporary hardness. See, don't capture that term first. We are going to capture it here. Now, before I capture that, you saw I wrote the word called scum. Listen, when you add soap to hard water, have you ever washed with borehole water? The patient has never. Have you ever got water from a well and washed with it? See, that means this is going to be our project. We have now many projects, preparation of carbon dioxide. Now we want to look at well water, spring water, lake water, tap water, rain water, and we add soap to each of them. See, we can add soap to each of them, shake for like 30 seconds. We compare which one formed the leather easily. Now we are seeing here, listen, when you add the soap to hard water, if you are using, some of you have not used the well water or borehole, what happens is that if you put, even when you are using the bar soap, you'll try to put a lot of soap, but you are not forming, you know what? You are only seeing white things. In fact, you'll be seeing white substances. And those substances is what we are calling what? Scum. Scum is a substance formed when soap reacts with hard what? Hard water. When you wash it with your shirt, borehole water, you'll realize that there are some white patches everywhere after the shirt has dried. White patches. See, that is scum. Now, listen. Scum is not calcium carbonate. Don't capture that bad. I've explained the scum. Scum is soap plus hard water. You get scum. See, and the scum, we are going to give it a chemical name later. That the product formed from soap and hard water is called calcium stearate, which is scum. That soap plus hard water, you get scum, which is calcium what? Stearate. Yeah, that is the chemical name for scum, calcium stearate. Soap. Now, because you are learning, we shall not refuse to give you those names. Soap is sodium what? Stearate. Then, why do you think you will receive calcium stearate as scum? That white substance formed in water when you are using soap on hard water. Why do you think it's called calcium stearate will form? Soap, sodium stearate plus hard water. Hard water is one of those calcium salts. That calcium salt makes it to become calcium stearate. Okay, we have explained that under soap. That scum is those things that form when leather has refused to form. Now leather will form after some. It will not refuse permanently. You will apply a lot of soap until the soap has removed all those salts. Then it will now be free from salts and form for you leather. Now temporary hardness, see, is removed, see, by we said what? Boiling and also is removed by, you talked about distillation. Distillation. So this one is majorly used to remove majorly the other type of hardness. It's not preferable here because there is a very big chemical reason there. That this is better removed by physical method called what? Boiling physical method. Then chemical methods for removing temporary hardness, chemical methods for removing temporary hardness here, we add washing soda. Addition of washing soda does it. Addition of a solution called what? Ammonia solution. Then addition of calcium hydroxide solution. And calcium hydroxide solution, we have been saying that is what we are calling lime what? Lime water. That you can add lime water, then water will become temporary hard. Will become soft after, when it's temporary hard, when you add those things. See, let us try to summarize with removing permanent hardness from water. How do we remove permanent hardness from water? That's temporary. That's physical. There is no chemical substance being added. Therefore, we call it a physical method. You see, this was called a physical because it is not involving any chemical substance being added. Removing permanent hardness, physical method is distillation. Distillation. Then the chemical methods, addition of a washing soda, removing permanent hardness from water. You add washing soda or you add soda ash, or both work. Washing soda and soda ash do the work. See, we say the adding washing soda or soda ash, then adding what we call sodium permutite, which is what we call as an ion exchanger. Yeah, you can do more research on them. Yeah. Now let us try to be in summary. To look at the uses of hard water, and finally we shall compare hardness. How do we compare hardness of borehole water, tap water, etc. Yeah. Now, uses of hard water. Is that water really useful? I think you're seeing that all the water used at home has some degree of hardness, because not rainwater nor distilled water. Used in cooking. Yes, washing, cooking, washing. And some people like to taste hard water. Has a good taste. Yeah. Does it have, yes, Kirabo?
Hard water can also be used for industrial.
Industrial purposes, like brewing waraj or marwa. One use, household activities, not so? Good for drinking, because it contains salts of calcium which do what? What does calcium do to your teeth? Yes, strengthens the teeth and the bones. See? Then used for industrial purposes like brewing, not so? Yeah. Now, it's because these days you see we stay in towns, but people in the village really suffer. They don't suffer per se, but you'll see that their cooking utensils inside, they look funny. See? Some have as if their inside is coated with a certain color around a certain region, around a certain middle part of their saucepan. It has a certain color which even you wash it can't go away. See? Yeah. It's because for us, we stay in town, we use steel wire, is it steel wire? To wash the what? They have leaves. A rough skin. See. Okay, now we can have now disadvantages of hard water. Is that water disadvantageous or it's not? See. Give me the obvious disadvantage there. It wastes soap. See, fine, wastes soap. Next, your clothes are, I don't know, it leaves scum on clothes, which are the white marks. Scum, white marks. But now, if you go and get borehole water and pour in a percolator or a boiler for water, you really see what those coils that are used inside those instruments will receive a certain rusting called the boiler scale. That hard water causes a boiler scale in boiler instruments. See? Yeah, that rust, that even if you do what, you can type in boiler scale on Google, it will show you that kind of rust. See? Then far in saucepans, boiler scale in boiler instruments. Then far in saucepans, far is that how do you call that? That lining that stays on those village saucepans. They are not village saucepans, that rusted region that never gets away. Now, hard water leaves a boiler scale in boilers, in instruments that have those heating elements in them, like percolators. See. Now, it also leaves far in saucepans. See. Scum on clothes. Now, let me speak a little on how do you compare hardness in different water samples. Then I'll let the lesson end there, and that will be the end. Comparing hardness in various water samples. In various water samples. This one I will ask you to demonstrate at home, maybe at your home. At your home. But I'll demonstrate in one test tube here. We shall access, but since you don't have a test tube at home, you can use cups and a few drops. Like now for us in the laboratory, we would have various water samples, have test tubes placed in the test tube rack, containing various water samples. We can put here tap water. We can put here the same amount, well water from a well. Then put here rainwater. I can also put I can put seawater. Okay. Now we add to this. To each you add a few drops of soap, liquid soap. You add a few drops of liquid soap to each water sample in a test tube rack. You add here, you shake for 30 seconds and see if it forms leather. Put here the same amount of drops, shake for 30 seconds and see if it forms leather. Then you compare the ones that formed the leather and how much leather it has formed. And it will show you that one is harder than the other, more hard, one is soft, one forms leather easily, one takes difficulty to form leather. Okay, you can compare like that. Then also we can find out whether water is temporarily hard or permanently hard by boiling. That means we can design a simple experiment. If I wanted to know whether water is temporarily hard or permanently hard, get water before boiling it and add to it, get water and add to it a few drops of soap solution, shake. If it doesn't form leather, boil, then add soap again and shake. You realize that if it is temporarily hard, it will form leather after boiling. If it is permanently hard, it can't form leather even if you have boiled. Yeah. Now we shall not do much beyond that. Let me give you the activity of integration, and we shall have the lesson ended there. Write this activity of integration. One way activity of integration, one way of reducing the effects. One way of reducing the effects of carbon-based fuels on the environment. One way of reducing the effects of carbon-based fuels on the environment is by switching to environmentally friendly energy sources. Is by switching to environmentally friendly energy sources. Any option that can be used, to convince, an option that can be used to convince the population to switch to new energy sources to switch to new energy sources. Is by designing stickers. Is by designing stickers or which the people who have by designing stickers which the people who have converted to new energy sources, people who have converted to new energy sources can put on their cars, can put on their cars, can put on their cars. Design a set of stickers that can be used to make other people think. Design a set of stickers that can be used to make other people think. Think about switching to other eco-friendly, switching to other eco-friendly energy sources, eco-friendly energy sources. Now we shall end there. Now in the review of what we've covered, let me summarize to you in a few minutes. Since we started, here is a long topic. We looked at several subtopics there, and we saw allotropes of carbon as the first subtopic. Then various allotropes, how we made the charcoal, how we make animal charcoal. Then we went to graphite, diamond there. Then we visited the fuels. We saw what's a fuel, sources of fuels, and we saw that the key important fuels are those that are carbon based. And we saw that to know that it's carbon based is to burn with the soot and leave a black residue, or sometimes ash. Now we looked at the effects of using carbon-based fuels like petroleum products, and we saw greenhouse effects, smoke, and other air pollution effects. Then we went to the carbon cycle. We looked at how carbon is interacted in the how carbon can move from one agent on Earth to another, though not moving as carbon direct, but can move in form of carbon dioxide, and also carbon direct if eaten if animals eat plants. We visited hard water, and we've ended with hard water through the types, through the advantages and the uses of hard water. And I thank you for being very, very good students. Till we meet in the next level of O level, that's senior 3.